with the webinar. It looks like we have a critical mass of attendees. My name is Shaish Shambori, and I'll be guiding you through this webinar. I know some of you are familiar with me. I've taught multiple training classes in the past and also delivered some webinars before. Today we're going to be talking about Creo simulation and more so in particular some of the things that you can do with the advanced simulation extension, or I guess you could also think of it as some of the more interesting topics that the average casual user typically would not delve into, but you can use Simulate to perform those analyses, and they can come out pretty beneficial. So as I get started here, I know some of you are going to have multiple questions as time goes on. If you have any questions, over on the GoToWebinar panel on the right-hand side, there's a questions pane. You can just type in your questions right into there, and at the end of the webinar, we'll take a look at those and answer any questions that have come up. Okay. So let's see here. So some of the features we're going to cover basically, or the majority of it is going to be looking at design studies. And so what are design studies in Creo Simulate, and what particularly do those mean, and what are some of the best practices when it comes to defining those design studies and then running them to get some more insight on different what's it called, measures in your analysis. And then we're going to highlight contact analyses, and so basically being able to simulate snap fits or have multiple components to form relative to each other. And then lastly, I'll highlight the fact that you can queue multiple runs and have them run sequentially with each other using the MEK Batch feature. And then and then after that we'll go into a Q&A, and then that'll be the end of the demo. Now, just a quick introduction about boundary systems. So when it comes to consulting and product development, we're basically one of the leaders in our field. We've basically done it with a lot of the big name companies, and everything from data management, CAD consulting or simulation, and also 3D printing as well. And just to give a quick highlight is, we basically made the Inc. 5000 list of fastest growing companies in the U.S. For the last 4 years in a row, and we've also made the Weatherhead 100 list 3 years in a row as well. And so when it comes to us doing what we do, we know how to do it pretty well. All right. So the first thing to talk about or to highlight in this case is going to be the design studies, and really a lot of users don't commonly use this, being that it's not one of the first things you click on, and sometimes it's hidden down below, and sometimes you may not really know what to do with it or how to use it. But really, it's basically you can use it to understand the effect of changing any design parameters and how that affects your analysis. And not only that, but you can also set it up for goal-oriented simulations. And so not only can I figure out, okay, if I change the radius of this fillet here, how does that affect my mass? You can also figure out and say, well, have simulate, run based on a specific target. So in other words, get me the lowest, mass part that meets a particular stress criteria. And in that case, instead of you sitting at the computer, setting up the analyses, Simulate will automatically change the default variables and then run the analysis by itself, and keep on doing that until it hits that goal. And next up, we're going to highlight is basically using contact analyses, and with that, that's basically in a case where with typical FEA analyses, the assumption is that everything is basically bonded or superglued to each other. And so if you have an assembly of multiple components, all those different components are superglued to each other. Well, if you have a case where that assumption is invalid because that's technically not true in reality, the way you would account for that is by using contact analyses. And one of the applications for that is in simulating, for example, snap fits. And so we'll basically show you an example of how to do that, where you can now begin to simulate more real-world applications when it comes to, okay, I'm pushing this component against this other one, how much force is experienced and how much stress does the other part experience as well. And finally over here, we're going to talk about queuing or using the MEK Batch functionality. And basically, this is one of those nuggets that's somewhat hidden inside of Simulate, but when you can use it, it's definitely very valuable. And basically, it's the fact that Simulate can automatically generate the code to run itself, from the command prompt. And so that way you can stack multiple analyses on top of each other and then run them sequentially. And once Simulate is done with one, it then moves on to the next one. And I also had a tip about that when it comes to using MEK Batch analyses to optimize your system resources whenever you're running the analysis. Now, at this point, I will pause for a second, and I know I didn't get a chance to do this beforehand. We have a couple of poll questions just to get a feel for the audience and your experience so far with simulating, what you've done or what some of your challenges are, or what kinds of simulation problems you typically tackle. And so I'll launch 3 different poll questions here, and I want all of you to pick the most applicable responses. Okay, so basically in this case here, how do you currently simulate your designs, and if not, yeah, is it every design, or I don't know if you have the time to do it, or you just don't even know how to simulate and you want to get into that. Now we'll wait on a couple more people to vote in here before we close that poll. Okay, looks like we got a pretty good response for that one. So we'll close that. Now, next up, the question pops up, and this here basically is what kinds of simulation challenges do you typically have whenever you're running a simulation? So is it that you don't know what all the different picks and clicks are inside of Creo Simulate, or whenever you try and run, you get a lot of errors, or sometimes you don't even know how to set up the model. Now, if it's a case of other, what I would actually like you to do is in the chat window at the bottom of the GoToMeeting panel, you can just expand that and type it in there. So if it's not one of the 3 that I have in there, you can just type in the chat window, I usually have problems doing X whenever you try to simulate your models. Okay, so we've got a pretty good response here. A couple of people mentioned, that you don't currently have Simulate, and one of the things you're looking for is to see what features are available or even possible in Simulate. And it looks like it's a pretty even split between not knowing what the buttons are to getting a lot of errors. Okay. And so we'll close that poll, and finally, just to get an idea of what kinds of technical challenges you typically face, this basically asks, what kinds of simulation problems would you typically be facing? So, is it just a linear static analysis, or you do a lot of fatigue, impulse analyses, or do you just have a lot of thermal analysis where you're heating something up and there's going to be some thermal expansion? And we'll give this a couple of seconds here to load up before we continue. Okay, looks like we have critical massive responses here. A good number of you mentioned that that you basically use Simulate for snap fits or assemblies, and also for linear static analyses. And then the rest of you, checked into the impulse analyses and also fatigue as well. Thanks so much for that information. That just gives a little bit of an idea of what you guys do. Now I'll pause here for a second and show the software here and show the demo. And before I do that, actually, one of the questions that was asked at the bottom over there was using Simulate, or I guess trying to figure out a way to do CFD simulations to map temperatures inside of a structure. And while that's a simulation application, that's not something that Simulate currently does. There's no CFD capability inside of Simulate to figure out the flow of fluids, but there are other third-party applications and packages that integrate very, very well with Creo Simulate, or I guess with Creo Parametric in general. And so an example of that is Autodesk Simulation CFD. And in that case, they actually have a plugin that fits right into Simulate, where you can just click a button and that pushes your model straight from Parametric into the CFD environment. You can set it up there, run it there, and you can get an understanding of what your temperatures are. But again, this webinar is not going to focus on the CFD application. It's going to focus more on the Creo Simulate linear and also nonlinear contact applications. Just wanted to address that as an aside there before I get into this. So first off, we're going to talk about the typical simulation process, and also how you can then use the design studies to improve the design. And so what we have here is a typical mountain bike that was designed in Creo Parametric. And now what we're then going to do is to say, okay, well, there's this particular component right here, this brownish component is what we're interested in optimizing. And so we can take first off, what we'll do is we'll open that component on its own and then start to take a look at that even more. Now, that entire mountain bike, was created using Creo Mechanism, and so you can then run mechanism analyses, on that model. And one of the benefits of using Simulate then is because of how it's, integrated with Creo Parametric, you can basically then import loads from one, application of Creo to another. And so in this case, you can basically take all of those loads from the connection analysis, so all the different reaction forces it was experiencing, and then import those into Simulate and have Simulate report and place those forces at the correct locations. And so again, basically what we just did there is prior to this, we ran a mechanism analysis to figure out, okay, due to as you have rigid body motion, how does the entire mechanism move dynamically? And then with this here, what we're then checking out to see is, okay, the maximum loads, at each of these particular areas here that each component experiences. Let's apply that to the model, and then see how stressed the model gets during that mechanism motion. Now, in this particular example here, we're starting out right around 170 grams, give or take a couple of grams, and so in Simulate, it's basically as simple as setting up your loads and your forces, and if you have constraints, you can set up those constraints. In this case, we're going to run without constraints, and then you set up your material properties, and finally you have to have geometry, which in this case you would have geometry, and as long as you have those four things, you can basically get into Simulate and start running a Simulate analysis. Now, in this particular example here, we're then going to go ahead and see here. When it comes to defining a static analysis, basically all you would need is just to specify if you don't have constraints. So in this case, where you don't have any constraints set, you can check this box for inertia relief, and that basically runs the model without constraints. And then next off, you can basically specify if you want it to be single pass or multi-pass. Typically, single pass will get you, for the most part, a very good percentage of the way where you want to go. It's very, very reasonable, and it doesn't task your computer as much as a multi-pass analysis does. And once you're done with that, you can just hit OK and then run the analysis. Now, in this particular example here, what we'll do is we'll take a look at the results of this baseline analysis here. Let's do this. And give me a second here while I set this up. So basically, we set up the model initially as it was, taking in those loads from mechanism, loaded the model, and this is what we get. So basically, I have hot spots right around that neck over there, and my maximum stress is about 62 megapascals. Now 62 is technically fine, but that's a little bit of a problem because my allowable stress is actually 38 megapascals. And so what I want to design this for, after taking into consideration our factors of safety and other considerations, is 38 megapascals, and so 62 is already overshooting that quite a bit. And so I now have to figure out where to add material in order to get this to meet the allowable stress limit. And this is where the beauty of Simulate comes in. One of the things you can do with Simulate that's not typically done often is to visualize the results a different way. So if I go here, I can create a different way of viewing this result, and in this case, what we'll do is we'll view it by the stress levels, and now basically what it's doing right here now is it's showing you all of the elements that are at 50% and above the stress level that you have, and so in this case, anything above 30.5 megapascals is colored, and so right here, I can see very clearly where my hotspots are in the entire model. And then as I dynamically change this, now it then begins to fill in the rest of the model. And so I can see first off that my hotspots are right around that neck right there. And also, if I remove a lot more material, right around that neck right there, and also right around this bottom neck over here at the bottom here where I have those red areas, right? And then next up is as I begin to fill in more material, one of the things that happens that you'll see is the last place to get filled in is this middle section right here. And so those are some of the least stressed elements in the entire model. And so not only does it tell me where my hotspots are, but it also shows me where I'm not really having that much stress. The material is not really bearing that much weight. And so now, if I then want to say, okay, well, let's go ahead and see how I can improve this design, I can do a couple of things here. I can do a couple of things here. First off, I can say, well, let's take that section in the middle there that didn't have as much stress in there. Let's go back into Creo parametric and let's cut a hole into that. So that way, yeah, so that way, I can save some weight, and I can then, run my analysis. And so right now I'm at 135, grams. Now I can go back into simulate and rerun the analysis again. Now in this case, what we have is the improvement run that was already created. And in this case, if I show the results from this, what basically comes up is, is this right here. So you'll notice we chopped off, a huge chunk of the middle section, and the stress only increased by, I don't know, 2 or 3 megapascals. So technically, I can save a lot of weight and not dramatically increase the stress in the model. I'm still not where I want to be. I still want to be much less than that, but at least I know, I can make this lighter by, hollowing out the middle, and I'll still be fine when it comes to, and I can still not drastically increase my stresses. Now here comes the fun part. Here comes the design studies and chasing down the stresses in here. And in order to do that, we'll do a couple things. First off, we'll take a look at the standard design study. Now what I just did is I just went into Creo parametric before this, and I added this extra hole in here, and now it gave me that. Now what I want to do next in order to figure out these hotspots is to optimize the dimensions of this radius right here. Now, typically how you would do that is you would go back into Creo parametric, type in a new dimension value, come back into simulate, and then run the analysis, right? Which technically you can do that, and that's fine. But another way that we can then do this is to say, well, let's use a standard design study, and I can pick a prior static analysis to reference, and now I can tell simulate I want to pick a dimension. I'll pick this dimension here, or that radius of that neck right there, and I'll say currently it's set to 11. What if that dimension was 20? Now I can hit OK and have simulate run the analysis, and it'll show me the model where that dimension is set to 20 and what the stress output is. And so it basically, what it basically does is it'll take the analysis as it is, pass it into Creo parametric, where parametric regenerates the model, and then passes it back into simulate for simulate to then solve. And so all of this it does in the background without you even having to have any input in terms of switching back to parametric or simulate. And the good thing about this is you can have as many dimensions as you want for as many different features. And simulate is fine with having all of those in there. And then the last of all, the final benefit of this is, say for example, I say, okay, what if this is set to 20? If I take a look at the result and I see that the new value I set it to is actually worse, it does not change my initial model. So the moment I hit cancel, my initial model is still set to 11. And so technically then, if I make a simulation change that makes the geometry worse, or I guess a geometry change that makes the simulation worse, it doesn't. I can always go back and get my old model that was not as the unit that was still better off. And so in this particular case here, what we have is I'll take a look at the results of this this analysis here, and what pops out is this right here. So I said, what if we increase that radius from 11 to 20, and simulate comes out and says, well, if you do that, your stress drops down to 38. So I'm right on. I'm on the right track. I'm basically increasing that radius. Gets me a huge drop in my max stress level, and I can begin to see, or I guess get an understanding of what how those dimensions affect my model. Now, another thing you can do is, instead of just getting a one snapshot in time of what if this dimension is a certain value, you can also create sensitivity analyses. And with that, what that is where you can basically take a particular dimension. So say, for example, instead of that top one, we'll take the dimension for this neck at the bottom, and we'll say, what if simulate have this dimension anywhere between the 4 and 10, and subdivide that 15 times, and run the analysis. And so what Simulate will do is 15 times between the values of 4 and 10, it'll pick a dimension value, run the analysis, and then regenerate again, pick a dimension value, run the analysis, regenerate with parametric, and it'll keep doing that over and over again until what I then have is a graph that I can then basically create and map with any measure that I want. And so, for example, in this case, I can see here, as I change that dimension from 4 to 10, this is a plot of my maximum stress in the model. So again, this is something that you would have to sit there and click through multiple times and wait for hours to get all of this data, or you can just program this into Simulate, hit the green flag, and Simulate does all this for you in the background. Now I can get an understanding of, okay, I get a huge benefit anywhere between 4 and about, 7. Between 7 and 9, there's not much, that big of a drop. There's some drop. It's not as huge. And then between 9 and 10, it's almost like there's a stagnation point or a stationary point, right? All of this information, is not something that's readily intuitive, but it's something that you can generate from Simulate by running sensitivity analyses. Next up is we'll show the results of some optimization studies here. And now with that, basically, again, that's going a step further. With an optimization, or I guess you can run it a couple different ways. You can run it as a feasibility or as an optimization. And with a feasibility, basically what that is to say, okay, let's set your design limit to a particular value. So say, for example, I want the maximum stress in the model to be less than 38 megapascals as that's my allowable. And I can then give Simulate any set of dimensions. I can say, okay, if you want to change, the width of that ellipse in there, you can change that anywhere between the minimum and the maximum. If you want to change the length, you can change that anywhere between the min and the maximum. Likewise, if you want to change the radius of that neck over there, you can change that anywhere between 10 and 30. And also the radius of this neck here at the bottom, you can change that anywhere between 4 and 10. But give me a model that has the maximum stress of under 38 megapascals. Now Simulate then goes and says, okay, well, I'll take that, I'll run the analysis, and it then comes out and then pops it out and says, okay, this is your model. It's under 38 megapascals of stress, and these are the stressed areas in the model. And the beautiful thing about Simulate, whenever it does that, is it basically knows what it's solving for, and so you don't even have to be there. If I take a look at the run status for this particular analysis, what we'll see is Simulate basically goes on and says, okay, well, I'll start with some initial numbers using these dimension values, and then it runs the analysis and it checks it and says, okay, I came out at 58 and I want to be less than 38, so I violated that. Okay, now let's start optimizing. Step 1, I'll change those dimension values and then rerun the optimization. I came out to 49. Yeah, I'm still greater than where I want to be. And so I'm going to continue. Iteration 2, I'm going to choose different values and keep going. In this case, I satisfied it within tolerance. And so it'll keep doing that until it converges to an optimal design where that meets your particular stress criteria. And so that's the beautiful thing about Simulate is that it gets you, you can basically set it up and let it run. Now in a case like this, it did everything in 4 analyses. And now you as a design engineer, you can go tell your manager, oh, I analyzed this thing 4 times, and this is the best thing we could come up with. And you look like a superstar, but really Simulate did all the heavy lifting. Now, not only can you also do a feasibility study, but we can also go one up from that and do an optimization analysis. And with an optimization, the additional thing you have in there is a goal. And so not only can you specify a limit to say, you must not exceed a certain value or you must not go below a certain value, but you can also tell it, okay, while you're doing that, also minimize a particular measure. So in this case, the total mass, for example. And so while you're getting me the least stressed part, get me one that weighs the least, a mass. And so now I can also add that in there and then run, have it run that and get me a model that meets that criteria as well. Now, whenever I do that and I run the analysis, what it then comes out to show me is this right here. Yeah. So simulate pops out and says, okay, well, based on what you've given me, I can actually, do you a couple more that's better. I can get your stress down to 34 megapascals instead of 38. And this is a least, or I guess this is the part that has the least mass out of, that you can generate and still be under 34 megapascals of stress. All of a sudden, I can see how I chopped a big hole in the middle of my model, but yet I have decreased the stress by almost a half. Now at the end of this here, I can, I'll close this, and the other thing about Simulate whenever it does this is that it saves an exact copy of the optimized model. And so in this case, whenever I go into that study, it has a folder there where it saves an exact copy of that model with the perfect dimensions. And so now you can open this up and see, okay, we initially started out right around 170, and the part with the least mass is right around 143 grams. So we basically saved, 16% of weight, and in order to do that, we dropped the stress by 40%. It's not every time you can say that. And so that's the beauty of Simulate and the fact that it's coupled with Creo parametric. You can basically do a lot of optimization and feasibility design studies that are pretty beneficial. Okay, next up is we're going to pull out an example here that's talking about contact analyses. And with regards to contact analyses, what we'll show here is basically this. So typically, we have in this case an assembly, and typically, I can then set this up to where I can, move one component into another. Now, again, in typical simulation language, if two components are basically touching each other, it'll always assume that they're super glued together or stuck together or bonded together, so their displacements will always be the same at that location where they're connected. Now, if they're not touching each other, and they will touch each other in the simulation, they'll basically pass through each other, almost like Casper the Friendly Ghost, walking through a wall. But then contact is the feature in simulation where you can basically specify that, one will bump into the other, or their displacements, don't have to be the same, but yet they can push against each other, and the forces can push from one to the other. Now, all of a sudden, whenever I have something like this here, I can then begin to tell Simulate, okay, based on what I have right here, I want to specify, a contact interface, and I can tell Simulate now, okay, this surface right here will probably bump into this surface right here. And so I can begin to pick all those references. And if I have any friction, I can specify if there's no friction between them, just as a perfect idealized example. Or I can specify in there there's infinite friction, or I can, which technically is a simulation assumption, or you can specify finite friction. And this is something they added in Creo 3. So you can type in there, okay, my coefficient of friction is, 0.8 or 0.5 or whatever it is, and it'll solve, using that value as well. Now, in this case, what we ended up doing is we have a model that's already been completely set up here, and if I go to that, okay, So this is the model that's been completely set up, and really the only thing is, we've gone through and defined all of the different surfaces that could potentially bump into each other. So for example, all these other surfaces at the bottom here that could potentially bump into each other, we've defined all of those contact interfaces. Now this, by the way, I forgot to mention, is this is a USB connector. So this is basically every time you stick your USB into your computer, this is an idealized example of a particular design of a USB connector where we have a symmetry plane down the left-hand side over here, and so it's chopped in half, which again you can take advantage of to reduce your simulation runtime. And all we have here is basically a constraint on this side telling Simulate push this yellow piece 0.21 inches in, and over on the back side over here, this is completely fixed. And so we're basically pushing the yellow piece into the gray piece. And now we can take a look at the results. And now these results are going to load for a couple seconds here because this has a fairly big results file. But when it pops out, it'll basically give us a very good understanding of how stressed the entire model is. So if I basically pull this in here, what you'll see is as my component is being pushed in, I can now begin to get an understanding of all of these snaps, and if those snaps are strong enough or too weak at their areas. I can take a look here and see, okay, that red spot right there, right around that neck, that could potentially be a weak spot depending on, again, my, the maximum stress level I have in my model. And so these are, again, some of the kinds of analyses that you can run in Creo Simulate and get very realistic stresses and values from. Now, finally, I guess I'll pause here for a second and actually show sort of a sidebar. Now, whenever you're running contact analyses, and really whenever you're analyzing with assemblies, one of the things that then comes into play is defining your interfaces correctly. And so what I'll do here is, right now this is a symmetry model, just a pi wedge of this green stamp over here on a plate, and that blue geometry represents the weld geometry, and this is going to go through a thermal simulation. Now, whenever now one of the most common errors that you will get in Simulate is an error that says the model is insufficiently constrained. And so, say for example, I have this the way it's currently set up right now. The constraint is acting on the gray piece at the bottom, but at this way, it's possible, depending on my interfaces, that this green piece or the blue piece could be insufficiently constrained. And one way for me to see that is I can basically go in here to the I can go here to review geometry. And basically what Simulate tells me is if any surfaces are super glued together, and so that means they have to move together, I'll color them purple. If any of them are contact, I'll color them yellow. And if any is free, I won't assign a color. It's just going to be transparent white. Now when I apply that, it shows me over here that the weld geometry is bonded to the plate and also the stamp, and likewise a stamp to both of them as well. And basically what this then tells me is if the plate is constrained, then the weld geometry is constrained because that's super glued to the plate and the stamp is super glued to the plate. Now if I then had a case where I did something like this, and I specified that as a contact, and then I also then add another contact interface between the bottom of that and this as well. Now, whenever I review the geometry, Simulate will pop out and tell me, based on what you have, this stamp over here is contact with the plate and the weld, which basically means it does not have to have the same deformation. It can deform on its own. Now, if I have this right here, I will almost certainly get an error when I run the analysis that says my model is insufficiently constrained, because technically right now this stamp can move up into free space for infinity and there's nothing holding it. And so this is a perfect example of how you can basically preempt some of those simulation errors by viewing the model this way. And now you can then go ahead and apply a constraint to this stamp in order to prevent it from moving as a rigid body in free space. And now finally, the last thing I was going to highlight is using the MEK Batch Studies. And for that one, what I'm going to show here is I'll go back to that first example we have, and I'll go ahead and take a look at some of these analyses here. So say, for example, we create a new static analysis. We'll call that analysis 3, and we'll say OK. Now, if we then want to stack these up, I can then create another one. We'll say that's analysis 4. Okay. Now we have analyses 3 and 4. If we now want to run these, what we'll do is, one of the ways you can do this is to use MEK Batch Studies. And basically what that is to specify that you want to run it as a batch. Now what this does is say I'll save this to the desktop, for example, and I can say save that. Yes, I want error detection. Simulate will then basically generate automatically the code that it needs to run itself from a command prompt. And so likewise, I can do that for this other analysis as well. And in this case, Simulate will then ask me, that MEK batch file exists. Do I want to append this new study into that file? And I'll say yes. And now when I do that, it'll also write that code into the same file as well. Now if I go to my desktop, what I'll see here is a text editable batch file with all of the necessary code that Simulate needs to run from a command prompt. And so now all I need to do is pick on that file on my desktop and hit enter. And once I do that, all of this passes into your command prompt and Simulate starts to run in the background. In fact, if I do it here just as an example, the only thing that happens is this window pops up. And once this black window is up, Simulate is running. You'll notice right here that analysis 3 is running. And the benefit to that is once it's done with one analysis, it'll continue on with the next analysis. And so this is a cool example where, I don't know, say for example that, on a Friday you can set up multiple simulation analyses, but you don't run them. And then at 4 p.m. on a Friday, you can, stack all of them up using that MEK batch functionality, and then start the file at the end of the day and go home. Now you can come back Monday morning and see, the fresh results of, 5 or 6 or 8 runs that you queued together. And the benefit to that as well is if you have a case where, for example, we set up, 5 runs together, and for some reason, the second analysis fails to run, or I guess the second analysis fails in the way it was defined, Simulate will basically skip over that one and run the next one. It will run the third. And so that way, it's not a case of, if one in the queue is bad, then the entire queue is bad. It just skips over that and continues running the next applicable analysis. So at this point, we'll flip back to our PowerPoint here, and basically, I just showed you a couple of different things. One of them, being using design studies to optimize your analyses. And next, I also showed defining contact analyses and being able to use those to simulate real snap fits and pressing one component into another. And then finally, I also showed as well the ability to use a MEK batch functionality to stack or queue your runs. Now, why does all this matter? Well, ultimately it matters because you can save time by understanding what your model is doing long before you build a physical prototype, long before you start manufacturing these models, and so that way you can basically predict the performance of your models. And not only that, but you can eliminate the need for spending lots more dollars on building prototypes. If you can vet out those prototypes and figure out by simulation which ones are the most feasible or most realistic. And then not only that, but even if you have a case where you're inherently over designing the components because you don't know what you don't know, well, with simulation you can then figure out, oh, well, we can probably take out 20% of the mass from this component, save ourselves 20% in material costs, and still not compromise our required performance. All of those you can figure out with simulation, and that's the benefit to this year, and that's why it's so sweet. Now, at this point, I'll open it up for questions. And so, if you have any questions, let's type them up in the questions pane at the bottom over there, and I'll take a look at those, and we'll take a look at them. Okay. Okay, so I have some examples here. I guess some questions here. One of the questions asks that the material is non-rigid and flexible. So, in other words, something like foam or rubber. So basically, non-linear material models. And they're asking, can that be simulated? And the answer for that is yes. Non-linear material models can be simulated. You can simulate the functionality for that is when you're defining the material properties. And if I open this up, I can show an example here. Let's see. So in the case where I'm defining a material, instead of having a linear stress-strain response, you can specify for it to be elastoplastic. Now in this case, this is where you're analyzing the linear plus yield in a typical stress-strain curve. And so this over here specifies a linear portion, and then this here would specify the yield or nonlinear portion. Or you can have it be hyperelastic, and this is what you're talking about, to where you have nonlinear material models like your rubber or foam. And you can basically just hit edit over here. And for some reason, I don't know why my simulator is not popping out with a table. Okay, there we go. Yeah, you can hit edit, and then this table will begin to type in there the uniaxial values of what the strain value was and what the corresponding stress that was seen. And typically, these kinds of tables you'll only get from either from what's it called, lab tests of the particular sample. But once you have this data, Simulate can extrapolate the coefficients, and then you can use that as a material model to run the analysis. Okay. Another question here asks, are the deformations accurate or exaggerated? It seems like the part is flexing a lot, even though the stresses are not high. And I believe that was for the bike example that I had. Yes, in that particular example, the deformations are exaggerated, and typically with if I pull this out here so you can see that. Yeah, so typically with when you're defining a simulated results window, the deformations are usually scaled up by 10%, which technically it's not a case of being shady or anything. It's really just a matter of showing you something that's visible enough for you to see. So in this particular example, if I take a look at the actual displacements come out to 0.04 millimeters, which is technically not, it's not big enough to where I can visually see that. But if I can scale it up to a percentage of the entire model size, then my model deforms more, and I can actually get a better understanding of where my model is deforming instead of just having to see something that's deforming by 0.04. Okay, another question asks, can Creo Simulate handle contact analyses between more than 2 components? And the answer for that is yes. Simulate can easily handle that. In fact, some of the more involved analyses that I've done with Simulate have been assemblies for the analyzing an axle hanger of a tractor trailer with at least 15 or 20 components where, I don't know, 3 or 4 of them are in contact with each other. And Simulate can handle those very easily. Okay. Now another question here is, do you have the ability to group the surfaces when trying to define a surface contact? Right now, there is no ability to do that. So basically, you would have to go ahead and pick all those individual surfaces. So you don't have the ability to group those surfaces. But what you can do, and this makes setup so much easier in Simulate, is you can create map keys to do all that work for you. So in that example that I have over here, technically I could go about picking all those surfaces one by one, or I can go ahead and create a map key. I can go ahead and create a map key, and I could say, for example, if I type in here, I don't know, say LL, now I can then record for Simulate to do something. So I can say, do this, specify contact, and I don't know. And then once you're done here, wait for me to pick the surfaces. And so now once I do that, I can basically start doing this. And so I can say pick the 2 surfaces, and then okay. Now all I have to do is press the map key button, and then begin to pick multiple surfaces. I can do that here, and then do that. And so it basically minimizes your mouse travel time, and you can just directly focus on picking those surfaces to set up. And so technically it's not as simple as picking those surfaces in groups and just specifying the contact between the groups, but at least it still saves you a good amount on mouse travel time by just having to press the buttons and it activating the command for you. Now, there's another question here about the friction of the materials. Now, with that, typically you should be able to, you would find that on the material specs. Now, you mentioned how accurate does it have to be in order to type in those values there. Technically, it doesn't have to be super accurate. One of the things, I mean, if you know the friction coefficient is going to be, 0.25, then you can type in 0.25 in there. But if it's something where you understand that that my model is that, it obviously friction is going to be anywhere between 0 and 1, and so you could just run 2 analyses, one where it's 0.1 and another where it's 0.9. And that can at least get you an understanding of the, least and worst case, or I guess the best and worst case scenarios for, how much force and how much of what you have to design for. And so typically you would find that with to the materials. But if you don't have that, you can still run it, using a worst and best case values in order to understand your design analysis. Now, are there any other questions with this? Okay, so it looks like the questions pipeline is dried up here. I really do appreciate your attendance at this webinar. I hope it was insightful and informational. And just to mention again, if you have any questions at all that haven't covered here, or if you have other thoughts or topics for things that we can cover in future webinars, my email is right there on the screen. You can basically shoot me an email to say, oh, for future reference, I would like it if you could cover, A, B, or C in future webinars, and we'll definitely consider those as part of future webinars. Thank you so much, and we'll close the webinar now. Thanks. Bye.